The small angle approximation fundamentally comes from the Taylor or Maclaurin expansion, which is something you hopefully learned in calculus, the idea that you can expand a function in terms of an infinite series of its derivatives. And I really love the Taylor expansion. The Taylor expansion of sine of x is one of my favorite things. So let's talk about this. Since it might be a couple of years since you've learned this, it might not be something that you're really comfortable with. So if we just think about the first term here, sine of x equals x, well, this is what that looks like, just x. That obviously doesn't really look like sine of x. But now let's add the second term. Let's say x minus x cubed over 3 factorial. That looks a little bit better. And so just to show you, the black line was that first term. The red line is now my first two terms. So this looks a little more sinusoidal, but it doesn't actually come back. Let's then add the third term, the one with x to the fifth. Now, again, not a lot is changing right here in the middle, but you see this wavy part of it. And if we go again, so this is now x minus x cubed plus x fifth over 5 factorial minus x to the 7th over 7 factorial, we again see this sinusoidal nature that again peters out. If we keep adding every single term, going on and on and on and on, we eventually will get back our sine curve. The blue curve is actually sine, and what you see is that this first line, the straight line, which was x, was okay right in the center. But as we added more and more terms, it actually got closer and closer to sine for further distances. So once you've gone out to, I think, x to the 7th over 7 factorial, it's now tracing out this first part really well. So I'm not going to remind you how to do a Taylor expansion or where it comes from, but the point I wanted to make here was that from the Taylor expansion, each of these higher order terms is a smaller correction as long as you're right around 0, that this was calculated around the 0 point, so that's where you have the highest accuracy if you're not actually going to include an infinite number of terms. So why am I talking about this, other than the fact that I really love it? Well, we actually need to use it here. And this goes back to having that differential equation that we couldn't solve. What you use here is called the small angle approximation. And the small angle approximation is going to be something that comes up in physics a lot, and this is the first place that it comes up, talking about a pendulum. So the small angle approximation keeps only the first term. It says that sine of x is approximately equal to x. This is only true if x is in radians. You cannot do this if x is in degrees. So that's really important. So here's a plot of what x looks like, right? Y equals x. It's a straight line. It goes through the point of, if I look 0, 0, goes through that point. You know what this line looks like. Well, how does that compare to sine of x? And again, we're zoomed in here. We're only looking at -1 to 1 radians. So if we then plot sine, so the blue line, the one that curves a little bit, is sine. The black line, the straight line, is x. Those are pretty close, aren't they? And obviously, as you get farther from 0, they get farther apart. So the small angle approximation is only valid for small angles. You can't use this for all angles. How small is small? Well, the book recommends using 10 degrees or smaller. And again, we always talk about radians, but I know 10 degrees is easier to remember. And so when we say small angles, we're looking at, say, this region, from -10 degrees to +10 degrees. And I've converted that into radians for you. However, you can see that it goes a little bit farther, still looking pretty good. So you have amazing accuracy under 10 degrees, positive or negative. You can push it out a little bit farther. But if you start using the small angle approximation for 45 degrees or 60 degrees, those aren't tiny angles. It's definitely not applicable there. So please keep in mind that if you have a pendulum problem or any angle where theta's, say, pretty big, where again, small is 10 degrees or smaller, 15 degrees is okay, 20 degrees is pushing it, 30, 45, 60, definitely can't use small angle approximation there. So that's what's going on here. We actually can get really close. Now, the Taylor expansion is something general in math, that you can do it for any function. And so we've been talking about sine of theta up till now, and I briefly want to talk about cosine. So how could we approximate cosine of theta, or x, for small angles. Again, remembering that we must do this in radians. So pause the video, select your answer, and then I'll tell you. Okay, so part of why I bring this up is that people frequently ask me, why sine and not cosine? Why do I love the small angle approximation for sine and not cosine? Well, because cosine is pretty stupid. That if you try to do the small angle approximation for cosine, the answer is that cosine of an angle that's really small is equal to 1. Now, that's really bad to work with if what you need is a relationship that involves that angle at all. So you maybe need to include the second order term, but that just gets really complicated. So I want you to remember that you shouldn't use the small angle approximation with cosine. That if you're setting that up, there's going to be a problem with your math later on. And so think about changing your original situation so you actually have sine of an angle. And so as much as I love my cat, this is Copernicus looking not very intelligent, so remember this stupid cat face whenever you go to do the small angle approximation for cosine. And remember, cosine is stupid, only use the small angle approximation for sine.